Hi, it has been quite some time, so welcome back. In the past, we made a series of videos describing how to create revision clouds. You can find the links to those in the descriptions. Basically, it works like this. If I go ahead and select a group of elements, it will add the revision cloud around them. If I run it, it will be something like this. So that's one of the limitations back then. Notice how as our generic model element family rotates, the curve will no longer follows the element because we're using the bounding box to generate these revision clouds. Therefore, it looks something like this. So today we're going to make that make an upgrade on that. Therefore, this time, if I go ahead and select all of these elements and run that, it will follow the original curve of these elements. Just like that. So you get these curves will follow directly along the element. So it's going to be different from, say, if I do this. It's different from this one. It's a lot more linear and a lot more accurate compared to whenever the element is rotated. And also, say here I have these building blocks have a angle compared to the default coordinate systems. And when our scope box rotate as well, this is how it looks on sheet. If we use the old script to create revision clouds around these elements, it will be follow the old or the default coordinate system, which looked really weird. But in here, in this settings, of course, because now they follow the model element curves. Now if I do that, this will look a lot better. But then maybe sometimes these ones are also at an angle. But for any kind of reasons, I still wanted to follow the I still want my new bounding box curves or revision cloud curves to follow the cropbox regions. I can do that by turning this on and run that. Notice this time the curves now follows the crop regions or scopebox curves, which will be following the curve of the building and now looks a lot more cleaner. So how is this done? Let's describe this using PowerPoint. So we have this element. When it's not rotated, the bounding box will be good, will be following the curves with what we use to create the revision clouds in the back. But if the element has been rotated, the default Revit bounding box will be much bigger in this case. And because it's taking the minimum x, minimum y, and minimum z to the maximum x, y, z. In this case, I want not this curve, but this curve. So we have the outline curves, and we want the inside curves. We want those 4 points. We know the outline curves by querying the Revit element bounding box, and we also know the theta here is the angle of rotation of this element. Here's how we're going to do this. Take that as x and y. Assume this is A and B. We have a theta, therefore that's theta and this is theta too. And then we get this distance equals A sine theta, because that's A, this is theta. Correspondingly, this equals B cosine theta. That distance equals A cosine theta, and this distance equals B sine theta. Therefore, we have x equals b cosine theta plus a sine theta, y equals b sine theta plus a cosine theta. We want to know a and b. We already know x and y. Therefore, a equals this, and b equals that. Now we know x and y and a and b. Let's translate this distance into point systems, coordinate. We have 0, 0, x, 0, xy, and 0, y. This is b cosine theta, 0 because that's on these angles, therefore that's 0, and this is b cosine theta. That's x, a cosine theta, because this is x, that's the x, and this distance is the new y. Therefore, that's a sine theta y, this is 0b sine theta. So we already know what is a and b, we know theta, we get these 4 coordinates, problem solved. Now let's take 1 second to think about what is the flaw in this equation. Here is it. If the theta is 45 degrees, sine theta equals cosine theta, and you're dividing something equals 0, and that's not going to work. And in the geometry world, I have this element rotated at 45 degrees. That's one possible. If I have this bounding box, there's another possibilities, and there's another possibility. I can create endless of possibilities. It's not gonna give me one single A and B equation answers. So how do we mitigate this? The first assumption is to, let's say this is 45 degrees. Let's not say that's 45 degrees. Let's assume this is something like 46 degrees. And what we get is this, the yellow curve, which is 46 degrees. So slightly away from the center of this point. And you can see that this is still very far away from this red curve, which is what we want. So the yellow curve is not going to work. And changing this angle is not going to work. So again, the answer to solve this is a pretty common method used in mathematics. If we want to deal with a question, and when we don't know the answer to that question, we translate this question to something we already know how to solve. So we cannot deal with this when it's 45 degrees. Let's just rotate the element a little bit more and draw the new bounding box curves. Now this theta is 46 degrees, and we can get that. It works. And this new curve, this green curve, we're going to assume that's the actual curve we want. And then we rotate the element back. You see the red curves and green curves slightly off, but the difference is really not so obvious. So we can just ignore that. Let's look at this in real work. So here I have these elements at 45 degrees, and I can go ahead and run that. Select, run. Oh, I have this turned on, align to cropbox. Therefore, these elements can be orthogonal. That's not good. If I turn this off and run. So what it's doing is rotating these elements by 1 degree and get the new bounding box, the new angle, calculate this curve, write this curve as revision clouds, and then rotate it back. As far as I can tell, it does not affect any of these angles, distance, or alignment relationships, but you cannot have it pinned. If this is pinned, which is here, you cannot rotate the pinned element and it will report something like this. So the ideal option would be to unpin it first, create a revision cloud, calculate the curves, and then pin them back. That will be the default approach, which here is not built in, just to show this. But the dimensions will retain, so it's good. It's a decent solution. And now let's talk about how this is done. How do I create, say if I go like not aligned to crop box. If I do not align to crop box, I will get something like this. And if I turn that on, you have that turned on, it will give me this. Don't know what's wrong with that one. Maybe it's wrong selection. So let's talk about how this is done. Again, we have some kind of rotated element. We have a exterior crop region or scope box. This is the default Revit bounding box, which follows the straight orthogonal x and y. This is the element bounding box, which is follow the angle of the rotation of the element, calculate according to the previous equations. What we want is the spread curves follows the crop region of the scope box. Now we already have this. Calculate that values. What we're gonna do is gonna take the old default 0, coordinate system, rotate it to along the red curves. And now we take these elements and map that to the new coordinate system. So these x, y's will be according to this coordinate systems. And then under that coordinate systems, the red curves is x minimum, y minimum being that point, x max, y minimum being this point, x max, y max at that point, and then x minimum, y max over there. So under this new coordinate system, the red curves will be governed by those 4 points. After we get those points under the new coordinate systems, we still get to rotate it back and map these new xy's back to the original coordinate system so that we can draw the curves. Basically, this is how it's done. And so let's look at this from the script's perspective a little bit before we go to the summary. Okay, So here is where we take the multi-element, go to a script to calculate the original bounding box curves, and if this is turned to true, run through this script to calculate the updated new curve following the new x-axis, and then using those curve corner point to calculate and create the revision cloud. Just like that. That's the active view. And let's look at a little bit deeper. This is the custom node. Here we take the element, calculate the rotation. If it is within 45, 135, 225, and 315, any of these are true, we take this rotation, plus it by 1, and set the rotation to that. Use those results to push in to get the corner point, x and y's, and feed in to do this calculation like we showed in the slides. Get the 4 point, and that will be our curve, the original bounding box curves. And here is how we rotate it. If we have a new x-axis, we'll normalize that vector, rotate this by 90 degrees, put it as the y-axis, and using this as the red coordinate system, if you remember from the slides. This is the default coordinate system, the blue one. We take the point list, transform that to get the new coordinate system, the new xy under the red coordinate system. And then there's the maximum x, minimum y, minimum x, maximum y, minimum y, those 4 points, just like the reverse calculation of how you get the bounding box. After that, the 4 point, you take the reverse coordinate transform it back, and use it as the curves that follows this new x-axis, which is the crop region box. So this is how it's done. Feed that into, create this into custom nodes, and make it happen. Okay. To summary, we have this, and what the benefit of that is create the accurate element outline, and this is faster. If you consider it, if I have any type of element, I want to know the outline of this. If we don't go this way, we'll have to query the element geometry. Now the geometry is very complex. Any family can have many different geometries. If you imagine a manufacturer-made Revit family, it will be a lot more details than the simple box that we are showing. Therefore, if you query the element geometry, it will take a tremendous amount of time if you're doing that across multiple elements. And using this method, it queries the bounding box, the rotation angle, which are both default parameters. So it works for all kinds of elements. You really don't worry about the geometry or any kind of family parameters or any of that kind. It's much faster compared to ask the element for the solid geometry. What it can be used, certainly create revision clouds, and doing, I imagine, gross footprint calculation, soft clash check. For example, I want to know what's within 3 feet of this element that I placed there. I can use it to create a 3 feet offset bounding box and get all the element that is inside that area, which will be a lot more accurate compared to using the default bounding box, which is always a straight square. Well, there are still some limitations. First, if it's 45 degree, you have to rotate it. Of course, linked element cannot be rotated, so you have to kind of ignore those 45-degree elements, which is a little bit bad. And secondly, I couldn't find the way to calculate the angle of rotation on annotations or text box. This is a little bit confusing, and hopefully some of you will provide me with ideas how to get the rotation on annotations. Again, and thirdly, right now it only works on floor plan because I'm just taking the shortcut to get the x, y's without trying to consider the possibility if the z-axis is not straight up ahead. But the same kind of concept will apply. You can easily modify the script to make it work on other type of, say, slanted floor plans or elevations. So there's that. Okay, this is it. This is how you create. This is the update version on the Revision Cloud scripts, and technically I think this is really overkill, but well, it's good to know. If it ever becomes needed, you can now create the bounding box or the revision clause directly follow the element outline. So if I do that, and let's take this to false and run, you get these points. Notice how I get the original bounding box from Revit, then get those 4 points, using those 4 points to create these curves, just like that. Okay, that'll be all. Thank you.